Welcome to This Explainer. Okay, today we are going to build complete conceptual mastery of a topic that, honestly, might sound just a little intimidating at first, but is actually incredibly cool. We're talking about coordinate geometry, and our core focus today? Uncovering the hidden triangles that literally rule our world. Seriously, this is the exact foundational science that allows engineers to build massive bridges, software developers to design your favorite video games, and GPS to actually track your phone in real time. So let's get our minds primed, get focused, and bridge the gap between algebra and geometry.
So I want you to imagine something with me for a second. Imagine you're trying to figure out the exact straight line distance between two distant towns. We'll call them Town A and Town B. But here's the catch. There are mountains in the way, dense forests, wide rivers. You absolutely cannot just walk the entire way in a straight line dragging a giant tape measure behind you. No way. So how exactly would you do it? How do surveyors and mapmakers actually solve this impossible problem?
Well, let's take a look at our two locations here, Town A and Town B. We happen to know that Town B sits exactly 36 kilometers directly east and 15 kilometers directly north of Town A. So we've got our horizontal distance, right? And we've got our vertical distance. All we really need now is that diagonal distance cutting straight across the landscape.
Now, you might not realize it quite yet, but if you're a 10th grade math student, you already possess the ultimate tool belt to solve this measurement mystery. You actually learned it years ago. I'm talking about our old friend Pythagoras. Remember that one? A squared plus B squared equals C squared. Because our east and north directions meet at a perfect, sharp 90-degree right angle, that direct, straight-line distance between the two towns is really just the hypotenuse of a giant, invisible right triangle.
Now, what is absolutely brilliant about this is how we can take a giant real-world problem, like distances between two entire towns, and just shrink it down onto a standard X and Y coordinate grid. Suddenly, everything is perfectly measurable. We can clearly see their horizontal and vertical distances as simple coordinate values sitting right there on the axes. And guys, this is the absolute magic of coordinate geometry.
Let's break this down visually. Imagine putting a magnifying glass right down onto that coordinate grid. If we plot literally any two random points in space, point P over here at coordinates x1, y1, and point Q up there at coordinates x2, y2. Now just drop straight perpendicular lines down to the x-axis. Then draw a horizontal line connecting them straight across. Bam! Do you see it? We just revealed a hidden right triangle connecting our two random points.
Okay. So to actually use Pythagoras, we need the exact lengths of the base and the height of this newly discovered right triangle. And it's incredibly simple. Just look at the x-axis. By simply subtracting the first x-coordinate from the second, so x2 minus x1, we find our exact horizontal base length. Boom! And doing the exact same thing over on the y-axis, subtracting y1 from y2, gives us our exact vertical height.
And this brilliantly illustrates our grand conclusion for today. That big, intimidating distance formula you see in the textbook, it is literally just our old friend Pythagoras wearing a clever algebraic disguise. Look at it. To find the direct distance, PQ, we just take our base squared plus our height squared and take the square root of that whole entire thing to get our hypotenuse. That's it. Base squared plus height squared equals hypotenuse squared.
But watch how beautifully this whole thing simplifies when we measure a point directly from the origin at 0, 0. If point P is just some random x, y, and the origin is exactly 0, 0, well, subtracting 0 from your x and y coordinates changes absolutely nothing, right? This gives us a neat, beautifully simplified shortcut. The distance from the origin is literally just the square root of x squared plus y squared. So clean!
All right, time to step up and apply our new detective tool to a geometric mystery directly from the textbook. We are given three specific coordinates, 3, 2, -2, -3, and 2, 3. The big question is, if we plot these 3 points, do they actually connect to form a valid triangle? And if they do, what kind of triangle is it?
So we just plug those coordinates right into our new formula, one pair at a time, to calculate the three straight line distances. Distance PQ comes out to the square root of 50, which is about 7.07 units. QR is roughly 7.21 units, and PR gives us a clean 1.41 units.
Okay, here's the crucial point where we test your Pythagoras knowledge backwards. First up, we know that in any valid triangle, the sum of any two sides simply must be greater than the third side. And because 7.07 plus 1.41 is indeed greater than 7.21, yes, we definitely have a triangle. But wait, Look a little closer at the squares. PQ squared is exactly 50. PR squared is exactly 2. Now, 50 plus 2 equals 52, which happens to be exactly QR squared because the sum of the squares of two sides equals the square of the third. We've just definitively proven this is a right-angled triangle. How cool is that?
Now, we can also level up this formula to solve for missing information. What if we want to find points that are exactly the same distance, or what we call equidistant, from two other locations? This isn't just textbook stuff. This is highly useful in the real world for things like determining a perfectly fair meeting spot between two cities, or even programming the boundary logic in a software application.
Let's look at this classic scenario. If an unknown point P, represented by variables x and y, is totally equidistant from point A at 7, 1 and point B at 3, 5, we can set up a seriously powerful algebraic equation. Because equidistant literally means the distances are equal, we mathematically state that distance AP is exactly equal to distance BP. Just set them equal. AP equals BP. So we write out the distance formula for AP, set it exactly equal to the formula for BP, and square both sides right away to just drop those messy square root signs. Now, as we expand those binomials, multiplying out all the x squareds and y squareds, and carefully simplify that algebra, something awesome happens. A huge chunk of the terms just cancel each other out. It beautifully simplifies all the way down to just x minus y equals 2. And what's truly amazing here is that this simple equation visually charts a straight line that acts as the exact perpendicular bisector between our two original points. Any single point resting on this line is perfectly equidistant from A and B.
We can actually push this logic even further. What if we need to find a specific equidistant point, but with a geographical catch? This point must be resting perfectly on the y-axis. Now, think about coordinate geography for a second. Any point resting exactly on the y-axis hasn't moved left or right at all, right? Which means its x-coordinate absolutely must be exactly 0.
Since we know for a fact the x-coordinate is 0, our unknown point is just 0, y. We can set up our equidistance formula one more time. We write out the distance from point A to our unknown point on the left side and set it equal to the distance from point B on the right side. And notice how we plug in a 0 everywhere the x-coordinate of our unknown point should be. By setting them equal, we can carefully, step by step, solve for our single missing variable, y.
So we square both sides to drop the radical signs again. On the left side, we get 36 plus a binomial expansion. On the right, we get 16 plus another binomial expansion. We carefully balance the equation, shifting all the y variables to one side and pushing the constant numbers to the other. Breaking down that algebra reveals 4y equals 36. Divide both sides by 4, and our y-coordinate is exactly 9, meaning our hidden, perfectly equidistant intersection point is precisely located at the coordinates 0, 9.
Think about what we just did. We started with an impossible real-world problem, jumping over mountains and rivers, and ended up proving right angles and finding perfectly balanced intersections, all without using a single ruler. By simply understanding that any diagonal distance is just the hypotenuse of a hidden right triangle, you have officially unlocked the power of coordinate geometry. So now that you've mastered the geometry hiding behind the algebra, what other invisible shapes and mathematical relationships will you use your new distance formula toolbelt to uncover out there in the world? Keep exploring, keep questioning, and I will catch you in the next explainer.
Welcome to this explainer. You know, coordinate geometry isn't just a boring list of textbook formulas you've got to memorize. It's actually this massive visual spatial puzzle. Today, we're going to build your conceptual mastery from the absolute ground up, treating the grid like a real-world map where every single number tells a specific story. Let's dive right in. So imagine you're an engineer for a telecom company, right? And you need to drop a brand new relay tower exactly between town A and town B. But here's the catch. It needs to be placed so its distance from town B is exactly twice its distance from town A, an exact 1:2 ratio. How on earth do we find the precise map coordinate for that tower without just totally guessing? Actually, our textbook kicks off with a really brilliant reminder in the note to the reader. It tells us that math literally has to link to your reality. It's not just alphabet soup floating on a page. It's the practical code we use to map physical towns, design video game physics, and engineer real-world structures. When we learn these formulas, we are quite literally learning the code to map out our physical world. All right, to solve our tower puzzle, I want you to grab your mental whiteboard magnifying glass. We've got points A, B, and our mystery point P somewhere in between. If we drop straight perpendicular lines down to the x-axis and across to the y-axis, wait, look at what happens. We just created similar right-angled triangles. By looking at these triangles, we're basically revealing the hidden architectural scaffolding of the entire line. And this brilliantly illustrates the sheer magic of geometry. Because those triangles we just drew are mathematically similar, their proportions are totally locked together. So the ratio of our main slanted line segment, that's the distance from point A to point P, compared to point P to point B, perfectly matches the ratio of their flat horizontal shadows on the x-axis. If the slanted line is cut in a 1:2 ratio, the horizontal base of our triangles is also cut in a perfectly exact 1:2 ratio. Make sense? Okay, let's translate that horizontal shadow into algebra. Think of this formula as the x-coordinate tug-of-war. Look at the numerator. We have our ratio parts, m1 and m2. Notice how they cross over? m1 reaches all the way across the line to grab the x-coordinate on the far right, x2. Meanwhile, m2 reaches back to grab the x-coordinate on the left, x1. You just multiply those pairs, add them up, and divide by the total weight of the ratio. And you know what the best part is? The exact same logical tug-of-war happens for the vertical distance. We literally just swap out the x variables for the y variables. So m1 reaches across to grab y2, and m2 reaches across to grab y1. It's perfectly symmetrical and honestly beautifully consistent. Put those two tug-of-war calculations together, and boom! You have the section formula. This right here is your absolute master key. No matter where your 2 points are on a grid, and no matter what crazy internal ratio you need to divide them by, this single, elegant formula is going to pinpoint the exact coordinate for you every single time. Now, the absolutely crucial step is knowing how to actually use this master key. Let's look at example 6. Think of this like following a baking recipe. First, you gather your ingredients. Your starting points are 4, -3 and 8, 5, and your ratio is 3:1. Now, we mix. We cross-multiply the x's, 3 times 8 plus 1 times 4, all divided by the total ratio of 3 plus 1, which is 4. That gives us our x-coordinate, 7. We do the exact same recipe for the y's, and we get 3. The precise point dividing that line is 7, 3. Pretty satisfying, right? But here is where things get really fun. What happens when we level up? In that last example, we knew the ratio, and we had to find the point. But what if we already know the coordinate point that splits the line, but the ratio itself is the mystery we need to solve? Well, if we just plug unknown variables m1 and m2 into our formula, the algebra becomes a complete nightmare. Juggling two unknowns is really tough. So your textbook introduces a literal genius hack. Instead of an m1 to m2 ratio, we just assume the ratio is k:1. By locking that second part of the ratio at 1, we squash our math problem down to just one easy unknown variable, k. Let's actually test this trick on example 9. We're told a line segment is divided by the y-axis, and we need to find the ratio. Here is the secret clue. Any point sitting directly on the y-axis has an x-coordinate of exactly 0. So we just take the x part of our formula, plug in our k:1 ratio, and set it perfectly equal to 0. When we solve that super simple equation, we find k equals 5. Boom, the line is divided in a 5:1 ratio. It's really that easy. Okay, let's pivot for a second. What if our telephone tower from the very beginning doesn't need to be closer to one town than the other? What if it needs to be exactly perfectly in the middle, like a beautifully balanced 1:1 ratio? Well, when your ratio is 1:1, something absolutely wonderful happens to the section formula. All those m1 and m2 multipliers, they just turn into 1s, and they effectively vanish. The whole thing simplifies into the incredibly elegant midpoint formula. You literally just add your two x-coordinates together and divide by 2, then add your two y-coordinates and divide by 2. You are quite simply just finding the exact mathematical average of the 2 points. Now let's look at example 8. The textbook asks for points of trisection. I know that word sounds kind of intimidating, but it's just a puzzle. Trisection literally just means slicing a line into 3 absolutely equal chunks. To do that, you need 2 slice marks, point P and point Q. For point P, you have 1 chunk on the left and 2 chunks on the right, so you just use your formula with a 1:2 ratio. For point Q, it's 2 chunks on the left, 1 on the right, so a 2:1 ratio. You're basically just using your master key twice. Next up, let's tackle example 10, which definitely tries to trick us by throwing a whole parallelogram at us. We are given 3 corners and a 4th corner with an unknown coordinate P. So how do we find it? Well, we unlock this using a hidden geometry rule. The diagonals of a parallelogram perfectly bisect each other. That means the exact middle of diagonal AC is the exact same coordinate as the middle of diagonal BD. We just use our elegant midpoint shortcut on both diagonals, set them equal to each other, and the mystery value of P just drops right out. So, to summarize section 7.4 and the whole chapter really, you have just built yourself a highly powerful coordinate geometry toolkit. You use the distance formula to stretch a mental tape measure between 2 points. You use the section formula to perfectly slice a line into proportional chunks. And you use the midpoint formula to find the absolute perfectly balanced center. You guys have absolutely mastered internal division today, but our textbook summary leaves us with a fascinating final thought to ponder. Everything we did today assumes the splitting point lies securely between our two original points. But what if the point laid outside the line segment? How would you conceptually divide a line externally? How would our formulas adapt to that spatial puzzle? Well, that is a mystery you'll explore in higher classes, but for now you have the foundational mastery to tackle literally anything the grid throws at you. Keep visualizing those math problems, and I'll see you in the next explainer.
So, I've got to ask you a pretty serious question. How many marks are you throwing away in coordinate geometry purely because of silly sign errors? Look, as a veteran board exam evaluator for the Karnataka SSLC, I'm going to let you in on a little secret. We actually don't want to deduct your marks. We really want to give them to you. But man, every single year I sit there with a massive stack of answer scripts, red pen in hand, and I just watch brilliant students bleed half marks and full marks on concepts they actually understand perfectly.
Well, welcome to this explainer. Today, I'm stepping straight out of the evaluation center and right into your study space. We're putting the textbooks away, okay? Because you already know what an x-axis and a y-axis are. Instead, we're opening up coordinate geometry, the evaluator's playbook. We're going to look exactly at how the official SSLC key answers allocate marks, where those hidden traps are, and how you can guarantee yourself every single half mark in Chapter 7. So let's dive right into this masterclass. All right, here's our game plan for today. First up, we'll secure those 1-mark MCQ sure shots. Second, we'll conquer the distance formula applications. Third, we'll break down the heavy-hitting section formula. And finally, we'll expose the notorious collinearity trap. Let's jump right into part 1, our 1-mark MCQ sure shots. Okay, let's start with the absolute quickest wins on the paper. These 1-mark questions, they're designed to test your reflexes, not your ability to grind through long calculations. You'd be amazed how often students completely overcomplicate them. For instance, in the 2022 main exam, there was this beautifully simple question. Write the distance of the point 4,3 from the x-axis. You would be shocked how many students started writing out the entire distance formula. Listen closely. The distance of any point from the x-axis is simply its y-coordinate. That's it. The answer is just 3. 1 second of thinking, 1 full mark. Similarly, if they ask for the distance from the origin to a point x, y, please don't write the long formula. Just write the square root of x squared plus y squared. Efficiency is absolutely key here.
And this brilliantly illustrates another classic examiner favorite. The question asks for the coordinates of a point dividing a line segment internally in the ratio 1:1. Now, when an examiner writes 1:1 ratio, they are directly testing if you recognize that it's just the midpoint formula. Please don't waste 3 minutes plugging m1 equals 1 and m2 equals 1 into the massive section formula. Just average the coordinates. x1 plus x2 over 2 and y1 plus y2 over 2. Boom, done. Move on to the next question.
Moving right along to Section 2, Conquering the Distance Formula.
Now, this is where your written presentation starts to matter immensely. As an evaluator, I like to call this the formula to points pipeline. The absolute second I see the correct distance formula written clearly on your paper, my red pen is already awarding you your first half mark. Literally. Even if your arithmetic completely falls apart on the very next line, you've secured something. So rule number 1, never, ever skip writing the baseline formula. And hey, you don't have to just take my word for it. Let's look at an official SSLC evaluation rubric. Let's say the question asks for the distance between points 8, 0 and 0, 6. See those half marks broken down? You get half a mark literally just for substituting the 8 and 0 and the 6 and 0 into the formula. You get another half mark for squaring them to get 64 and 36, and you get the final half mark for writing the final answer, 10 units. Every single step is a checkpoint for marks.
But here is the part that genuinely breaks my heart, the examiner's mark traps. These are the 3 exact places you're going to lose those precious half marks when exam pressure kicks in.
First trap, dropping negative signs. When x1 is negative, x2 minus x1 becomes x2 plus x1. Countless students mess this up. Second trap, you do all the math inside, you get to 100, and then you just leave the answer as 100 instead of the square root of 100, which is 10. And the absolute worst offense, squaring a negative number and getting a negative result. Negative 8 squared is positive 64, guys, not negative 64. Please, I'm begging you, double check your signs.
All right, into section 3, the section formula breakdown. Okay, now we're stepping up to the higher weightage battlefield. These are your 2 or 3 mark multi-step questions where organization is literally everything. On one side, we have the visual reality of what we're actually doing, finding a specific point on a graph that divides a line. On the other, the algebraic execution. Now, I know the section formula looks intimidating, m1 x2 plus m2 x1 all over m1 plus m2. It's a mouthful, but honestly, it's just a predictable pattern.
The really crucial thing for you to know is how we grade this beast. Take a look at this official key snippet for a 2-mark question. See the precision there? Just substituting the values, 2 times 4 plus 3 times negative 1 over 2 plus 3, that substitution alone earns you half a mark. Simplifying the numerator to 8 minus 3, that gets you another half mark. And the final coordinate pair, 1, 3, gets the last chunk. Do not jump steps. We cannot give you step marks if the steps aren't actually on the paper. To execute this flawlessly under stress, I want you to use this high-yield memory trick. Step 1. Write the coordinates out horizontally and write the ratio m1 to m2 right above them. Step 2. Physically draw arrows on your rough work. Cross-multiply. The left ratio number, m1, multiplies with the x and y on the right side. The right ratio number, m2, multiplies with the x and y on the left side. Step 3. Just divide by the sum of the ratio. This visual cross-multiplication trick stops you from mixing up your x1s and x2s when the clock is ticking.
Finally, section 4, avoiding the infamous collinearity trap. So let's address the most treacherous application question in this whole chapter. Here's a scenario that plays out every single year. The exam explicitly says, verify whether the points A, B, and C are collinear with the help of the distance formula. And what do students do? They remember that collinear points form a triangle with 0 area. So they write out that massive area of a triangle formula. It equals 0, they feel brilliant, and I have to give them a fat 0. Why? Because you didn't follow the instruction. If the board specifies distance formula, you absolutely must find the distances of A, B, BC, and AC and prove that the 2 smaller segments add up perfectly to the largest segment.
Check out the official rubric for this exact scenario. Look really closely at how it's scored. The evaluator is instructed to give half a mark just for calculating the distance of AB correctly as root 2. You get another half mark for BC, another for AC, and a final mark for making the concluding statement that AB plus BC equals AC. By doing exactly what the prompt asks, you are literally unlocking sequential marks designed specifically for you.
I really want you to keep this quote in your head the next time you sit down for a mock exam. Every half mark counts towards your distinction. As an evaluator, I promise you, I am actively searching your paper for reasons to award you marks. But you have to give me the raw material to work with. Write the formula, substitute clearly, watch those negative signs like a hawk, and whatever you do, don't skip your intermediate steps. 100%. That is exactly the percentage of these coordinate geometry marks that belong to you if you strictly follow this rubric logic in the exam hall. You already have the math knowledge, and now you have the evaluator's playbook. So the next time you face a section formula question, are you just going to crunch numbers, or are you going to strategically claim every single half mark waiting for you? Think about it. Good luck with your preparation. You've got this.